how it can then be applied to radio interferometry. And then two particular projects we've been working on lately with this intention of trying to take things closer to the realistic setting. So firstly, compressed sensing has been a huge development. So it's maybe 5 or 10 years ago now since these first papers came out defining the theory of compressed sensing. But now it's a huge industry. There's hundreds, if not thousands, of people working on this. There's a lot of new results, and applications are coming up in all areas. So a lot of medical imaging and also radio interferometry, which is what we're focusing on. So these are the two guys who are really the founders of compressed sensing. Although, as I say, there are a lot of people working on this now. So going back to the fundamentals of compressed sensing, it really comes from this idea of this mystery of JPEG compression, kind of along some of the ideas that Tobias was telling us about. That we take an image with, say, millions of pixels, if it's just a standard camera, but then we throw away a lot of this information. We do JPEG compression. So why did we bother measuring all of that information in the first place? So compressive sensing goes to the idea of the level of acquisition and says, maybe there's some way we can acquire the data in a slightly different way to try and capture all of that information without measuring every single pixel. So on one level, you can think of it in terms of the acquisition, but then the way you actually recover your image from those measurements is a slightly different process. So there's also these ideas of how do you actually do imaging. And so for radio interferometry, we want to focus on both of these things, I think. On one stage, the level of acquisition, how this could change our telescopes, these kind of ideas, particularly along the lines of this W-term effect, and also just the pure imaging. If we have our measurements, what's the best way to recover an image from those? So as I said, just to give you a quick refresher on compressive sensing. So there's a few very simple equations here, but I really just want to get across an intuitive kind of understanding. So we start with some signal X, decompose it into some basis of wavelets or Dirac or whatever. But we can really just write this as a simple linear transform. So alpha are our coefficients, say our wavelet coefficients, and this matrix here, psi, each column is just a particular basis function. So that's our signal model. And then we have some model of how we do measurements. So a very general model that's often used in compressed sensing is that a measurement is really just some projection of your signal X onto some measurement vector. So this is a very general way of modeling measurements. If our measurements were made by a convolution, then these basis vectors, these measurement basis vectors, would simply be translated versions of one another. And again, we can just write it all as a very simple linear equation where each row now is the particular measurement basis vector. So putting this together, we have our measurements Y are made by some linear operator applied to X, and X itself we can decompose into some basis or some dictionary. So here we can draw a picture of this matrix, of the system. We get, if we have an orthogonal basis, then we get a square sparsifying matrix. And if we're taking few measurements, so n, the number of measurements now is less than n, we get a fat sensing matrix. So we then had this ill-posed problem that I just showed you the picture of, where we want to recover X now from incomplete measurements Y. So compressive sensing results solve this by saying, well, firstly, this is an ill-posed problem, so we need to impose some regularizing prior. So it turns out that a very good prior is to assume that these coefficients, alpha, can be sparse. So if we've chosen a good dictionary here, then many real images can be represented very sparsely if you choose an appropriate basis. So what we do is we try and minimize the sparsity. So this is the L0 norm. The L0 norm is just counting the number of non-zero terms. But of course, we need to have our measurement constraint as well. So ideally, that's what we'd like to do. We solve this L0 problem. But it turns out doing that is difficult. So what we do is we consider instead a convex relaxation of that problem. So instead we consider the L1 problem. So we replace this L0 term with an L1 norm term. So this is just summing the absolute values of the terms. And this now is convex. So we can solve this problem with algorithms from convex optimization. And there are many very fast methods and accurate methods that can be used to do that. So we've replaced the L0 with the L1 norm. But it turns out that in many cases, the solutions of these problems are similar. So here I've showed this diagram of the geometry of the situation. When we're solving the L1 problem, sorry, the L0 problem, we're really promoting solutions along the axes. So remember, this is say we're just in 3 dimensions. So we just have, say, 3 wavelet coefficients. We want to minimize the number of non-zero terms. So we're trying to find solutions that lie where at least one or other of the coefficients is 0. So that's ideally what we'd like to find, solutions near the axes. If we think of the L2 problem here, then we have this plane, which is our measurement constraint, and we're trying to minimize this L2 norm on our error, which is just like the L2 ball, which is just a standard sphere. So we expand the L2 ball until it intersects with our measurement constraint, and we might find a solution here. Well, you'll see that this is not near the axes, right, which is where the L0 norm tries to promote solutions. However, if we look at the L1 ball, and do the same thing, often we will indeed find solutions that lie on the vertices of this ball, so along the axes. Now that won't always be the case if this plane is parallel to the edge of that L1 ball, but you can see that we do a much better job in general of trying to promote solutions near the axis. So this is why this is a good thing to do, this L1 minimization. So in the absence of noise, this theory is all exact. You can say exactly how many measurements you need to recover an underlying signal of dimension n. So the number of measurements you need depends on the sparsity. So k here is the number of non-zero terms in that basis. So here, this is a constraint for exact reconstruction. How many measurements do we need? But we can develop a kind of intuitive understanding by turning this around slightly and saying, well, we have a given number of measurements, and what we care about is the quality of our reconstruction. So you can kind of think of these parameters, instead of driving the number of measurements, as driving the quality. So if we have something that's more sparse, this would say we could take fewer measurements, so k would be smaller, you can have smaller m. But since we have a fixed number of m's, you can kind of think, well, if it's more sparse, we can do better quality in our reconstruction. But there's also this other factor that drives things, called the coherence. So firstly, let's just look at this, the picture of this system, try and get an intuitive idea of what this coherence is measuring. So the coherence is the maximum of the absolute value of the inner product of your sparsity atoms or basis vectors, so the columns here, and your sensing basis vectors, so the rows here. So really, what we want, so if the coherence is large, it's saying we take one of these basis vectors, when we pass it through this operator, for one particular sensing vector, we'll get a very large value. But for the others, it will be small. So it means that if we have large coherence, it means we can represent this basis efficiently in a small number of these atoms. So the alternative is, if coherence is small now, the inner product is small for any particular one, which means the energy of the atom is spread over all of these. And why does that influence our reconstruction quality? Well, if we think here of, so now we have these measurements y, we don't have a full set. And alpha are our wavelet coefficients, say. Many of these we think will be 0, and there'll be a few non-zero terms. So the non-zero ones are colored in here. But if we're going to have any hope of characterizing this full vector of dimension n, we better hope that when one of these atoms, one of these non-zero coefficients gets passed through the system, it's spread in y. If it just contributed to one element in y, then we'd have no way of recovering this full vector from just a small number of terms y. And that's exactly what the coherence is saying. Coherence is saying if we take one element here, that pulls out one particular vector, we want that to be spread. So we don't want it to be represented efficiently in just one term, in one sensing basis vector. We want it to be represented in all of them. So that's why the coherence is really driving the reconstruction quality. So just to summarize, with compressed sensing, we can think of the quality as being driven by sparsity. So the more sparse a signal, the better we'll do. And the less coherence between the measurement and the sparsifying bases, the better we'll also do. So all of this is robust to noise, and this is really the kind of first developments of compressed sensing. But there's been, a huge number of recent works and new ideas in this area. Okay, so now we can apply this to radio interferometry. It's very straightforward. In radio interferometry, we have a linear system. Y here are now our visibilities. We have some measurement operator, and X is the image we'd like to recover. So we can construct different measurement operators for the different problems we're considering. Say we have some primary beam A, we throw that in. We might have some W term, we can include that. Here for a constant W, a Fourier transform, and then a masking that encodes the discrete incomplete measurements that we've made. And so as soon as we've defined the system, we just solve the general problem that I showed you before. So we minimize the L1 norm. So we promote sparsity in this in a particular basis that we've chosen, subject to the measurement constraint. So there are various ways you can choose this sparsifying dictionary phi. You could use a Dirac basis in which you're it's like a point source model, so you can kind of think of that as being the equivalent of clean. You could use Dolbesch's wavelets, that's kind of the equivalent of multi-scale clean, or maybe a slight evolution of multi-scale clean. But also you can go further and consider different, slightly different ways of posing this problem, different types of dictionaries. And so in the next talk after lunch, Vio will discuss this further, and in particular this Asara algorithm that we've developed that goes along these lines. Okay, so now that's a review of compressed sensing and its application to radio interferometry. Let's think of now some recent evolutions to try and take this a bit closer to the realistic setting. So this W term introduces what's known as the spread spectrum phenomenon. That was first considered in this paper by Vio in 2009. So here I give an explicit expression for the W term, which I'm sure you're all very familiar with. So we have this type of modulation in image space. And just as we heard previously from Tobias, this W term actually can improve the quality of our reconstruction. So we heard previously that from theoretical grounds, this could provide us with more information content. So here in the context of compressed sensing, we can come up with an argument that shows, for this particular algorithm, why we also expect this to improve reconstruction quality. So remember, the quality depends on sparsity and coherence. And so the thing we play with here is coherence. So remember, the coherence was given by the maximum inner product of maximum absolute value of the inner product between the measurement basis vectors and the sparsity basis vectors. Well, now we're essentially doing Fourier imaging, more or less. And so our measurement basis vectors are just the exponentials of the Fourier transform. And so the coherence now is really just given by taking the Fourier transform of our sparsity vectors and looking at their maximum modulus. So anything that will reduce the maximum modulus of these sparsity vectors would improve the quality of reconstruction. And that's exactly what this W term does. So this W term produces this chirp effect, which has high frequency content. It's a modulation in image space, which means it's a convolution in Fourier space. So when we think of applying this to our sparsity basis vectors, it's performing a convolution. It's spreading the signal, hence the name, this spread spectrum phenomenon. It's spreading the signal, thus reducing the maximum modulus of the Fourier coefficients, thus improving the coherence, so that's reducing coherence, and then improving reconstruction quality. So we have an intuitive kind of theoretical argument for why this should help, but this has also been examined in the same paper by Vio on simulations, and indeed we see this improvement in performance. But in this work, just for simplicity, only a fixed W was considered, so W of 0, no W term, or a constant large W, which of course is not realistic, but it at least demonstrates the effect. So now we've been reviewing this in the context of varying W. So now we allow W to vary. And this is work that's been done by Laura Waltz at UCL, who's a PhD student there, who's done some very nice work investigating this. So we essentially use the W projection algorithm, so we can consider this varying W. We move this chirp type term past the Fourier transform in the measurement operator. So now we get the chirp term here. And now we can easily consider a different W for each UV measurement. Right, so we approximate that by a sparse matrix, which allows us to do this efficiently, but we're not going to extremely high resolution. So we're still idealized, but we at least have this concept now of varying W included. So we applied this to simulations to see what we get. So here's our ground truth image, this image of M31. And here is the performance quality we get. So along here we show different visibility coverages from 10 to 70% and the SNR of the reconstruction. This is for Dolbesch's wavelets, so you can think of maybe as similar to a multi-scale clean type approach. So the blue line shows the reconstruction quality with no spread spectrum effect. So so we have a discrete W here that goes from 0 to 1. So 0 is constant W, but no chirp. WD of 1 is the maximum W, but constant throughout. We get this red curve. So we can see that we get this large improvement in quality. But what is really interesting is that for this case now where W is allowed to vary, so for this simple simulation, we just allow this to be uniformly sampled from 0 to 1. And we find that the quality of reconstruction is very close to the full maximum W case, which is very interesting because that tells us that it's not, we don't need to have this constant large W. So long as sometimes W reaches these large values, we get almost the same improvement in quality. And this is for the case where we use these Dolbesch's wavelets, in which case the coherence is suboptimal. So we see an improvement, as we'd expect. For the Dirac basis, so just a point source basis, then coherence is already optimal. So in fact, the Dirac basis is optimal in terms of coherence relative to the Fourier measurement basis. So coherence is already optimal. We shouldn't really expect to see any improvement. And that's indeed exactly what we see in our simulations. So far we've just done one simulation here, and we're running many more simulations now to construct some error bars on these plots. But it seems, well, we've done a couple of one-off simulations like this, so it seems like these results should be robust. And here I just show a couple of images. So this is from the Dolbesch's wavelets case where we do get this improvement. This is with no W. This is with the large maximum W. We can see we get a dramatic improvement here. So this is really this point on the previous plot, 10% coverage. And this is now varying W, where the discrete W is uniform from 0 to 1. And we see that we do pretty well. Not quite as good as this case, but very close to it. This is plotted on a log scale, so you can really see these differences. So that's one thing we've been looking at. Another thing we've been looking at is support for continuous visibilities. So ideally, we'd like our measurement operator to just map from straight to the continuous visibilities, but obviously this is incredibly slow. So we've now incorporated a gridding operator into this framework. So this is work that Rafael Carrillo has been doing. And our measurement operator now includes G, convolutional gridding operator, F, a fast Fourier transform, but we also upsample in the visibility space simply by zero padding an image space. So this just gives us a finer grid in visibility space. And we want to undo the effect of this convolutional gridding. So we have an operator in image space that does this. So this is really trying to model this continuous operator as closely as possible. And here I'll just say that, again, quite idealized, simple simulations, but we have now some continuous visibility coverage, and we image M31 again with these visibilities. These are the reconstructed images for a range of different methods. So, I mean, this is more just to say that, this is something now we've added. we do actually very well with the SARA algorithm, which Eve will tell you more about in the next talk. So finally, just to conclude, there have been a number of works looking at compressive sensing for radio interferometry. I think these have extremely promising results. There's improvements provided in the quality of reconstruction, also in the flexibility of the methods, so you can easily add in additional priors, and also computation time. There's many sophisticated convex optimization algorithms that we make use of. But really, we now need to go a bit closer to the realistic setting. So we've made the first steps to do this, and now looking at spread spectrum with varying W, and really it's very interesting to see that, in fact, you don't have to have this large maximum W. So long as sometimes your W reaches a maximum, it makes a very large improvement to the reconstruction quality. And we've incorporated a gridding operator into our framework. But nevertheless, I mean, everything is still very idealized. Here we've been using MATLAB codes. We have very small data sets. But now we're trying to take this to a much more realistic. So now we're developing an optimized C code to really improve the execution time of the algorithms and also handle larger data. So this is something that actually we're quite close to finishing. Some preliminary tests have shown that this provides really a dramatic speed up compared to our previous codes, and we're able to now also go to very, very large data sets. So now that we have this, this kind of low-level C code, we're hoping to really start pushing this further and try and tackle real data soon. Thanks.